So, Sunday problem set was due 41 to 62. We'll start if there's questions anywhere in there or on previous things before we jump into the new stuff. Anybody got any questions? Emma? 56. Okie doke. So 56, we're asking to convert from polar to rectangular. Well, the formula is just for the x coordinates r cosine theta and y sine theta. So let me think here for a moment. Cosine of 60 degrees, that's 3 or square root 3 over 2. And for sine, that's 1/2. Or do I have those flipped? I forget now. Unit circle's hard sometimes, guys. Oops, wrong mode. Do you ever just... I flipped them. I knew it. Ah, boogers. So you might write it this way, or maybe you convert it into a decimal. Depends on what the directions ask for. Here, I guess it doesn't really say how they wanted it, so either I think is appropriate. Kenzie?
So if I split it in -3 cosine of 60
The directions don't say that you need to give an exact value.
Okay.
So I don't think that it just depend on what the directions asked for. Probably gave you a radical, right? In the answer. It freaked you out. Oh, this one didn't have an answer. But yeah, you just type it in, give it a decimal, it's fine. Not inappropriate for these directions. Amy, what's up? Sure, 60. So we need to convert this into polar coordinate. So I know that r squared is equal to x squared plus y squared. So when I square root both sides, that is the square root of 136. 25 plus, 146. 25 plus 121. And I don't know if that reduces. I don't think it does. And then if I graph this thing, 511 is like here. So this is my theta. So theta is just going to be the tan inverse of y over x. So I just type that into my calculator, and that's my r comma theta. Does that feel okay, Amy? Okay. Mackenzie? 58. Sure. I mean, it's the same thing. Just turn your calculator into radian mode. Right? And it'll just take care of itself. So that is just going to be 1/2, and this one will be -√3 over 2. Or if you wanted to do it on your calculator, if you turn that back into radian mode, you do cosine of -5 pi divided by 6. Oh my goodness, I flipped him again. Mr. Kulik, you're having a bad day. Oh yeah, because I'm in the wrong stupid quadrant, you dummy. Sorry. You ever have a bad day where it's just like, you think you're doing something right, and it's like, nope, you made a stupid mistake. Oh, you made another stupid mistake. Oh, you made another stupid mistake. And just like, just feel like you just in that cartoon where you're just walking through the front yard and you keep stepping on rakes and they hit you in the face.
Limason style.
Yeah. Yeah, something like that. Mackenzie, are you happy with what we did there, though? Yeah, I mean, it's the same thing as the other one, right? You just type it in your calculator, or you can use the unit circle if you want. Like, 6 1/2 dozen the other to me. Amers. 50. Do you need to plot all the points?
No, just like Y and C.
Okay. Just tack that on there somewhere. So y is 5/2 comma 10 pi over 3. So I notice that's more than 2 pi, right? So maybe I first knock that down to 4 pi over 3. Is that okay? And really, maybe it's easier to think about that as like 8 pi over 6, really. So like 1, 2, 3, 4, 5, 6, 7, 8 pi over 6 is that one. And I'm just going to count 2.5 circles. 1, 2.5 is like right over there. Is that okay? Oh, did I count wrong? 0, 1, 2, 3, 4, 5, 6. Yup. 7, so that would be 8. Thanks, Ella. And then which other one you said? Z or something?
Yeah.
So that's -6 and -9 pi over 4. Again, I'm going to go ahead and convert 9 pi over 4. I'm going to add 8 pi over 4. That makes it -1 pi over 4, and do it again. So that's +7 pi over 4, which is like 315 degrees, which is probably the easier way to think about it, since it's not going to be one of the grid lines because it's not a denominator 3 or 6 fraction. So this was 300. This is 330. This is 360. So 315 is going to be like right in there. Now, because this is negative, I know I'm going to have to flip it onto the other side. And now I'm going to count 6 circles down. So 1, 2, 3, 4, 5, 6. Looks like right over there. Is that okay, Amy? Yeah, so just remember that every one of the straight lines is basically 30 degrees or pi over 6. And that's, if it makes it easier to convert everything into degrees, convert everything into degrees and just handle it all in degreesies. If you're cool with the radians and fractions, and you can count by 6 or whatever, but it's just counting, you know what I mean? Even if the numbers get a little weird or whatever. Does that feel good, though? No problem. Anybody else? Okay, my dudes and deuterinos, and let's go ahead and get crack-a-lack-in here. Today, we're going to finish up chapter 10. So we're going to be talking today about polar functions and then some specific types of polar functions. So the first thing that we're going to be talking about is converting back and forth between polar functions and rectangular functions. The main tools that we're going to use to do that are the same tools that we use to convert back and forth between polar coordinates and rectangular coordinates. So those are the main tools to go from polar to rectangular. X is equal to r cosine theta and y is equal to r sine theta. And then to go back from rectangular to polar, we know that x squared plus y squared is equal to r squared, and then tan theta is equal to y over x. So let's do some examples of converting back and forth between polar functions and rectangular functions. So our first one, we're told r is equal to 6 cosecant theta. Now you should recognize right away that this has to be a polar function because it's defined in terms of r and theta. The convention for a polar function is that r is the independent variable and theta is the dependent variable. So the first thing that I'm going to want to do on this is I'm going to try to rewrite this in terms of sines and cosines. So I remember that cosecant is the same thing as 1 over sine theta. And then if I multiply both sides by sine theta, that's great, because what is r sine theta equal to? It's y. So this equation is just good old y equals 6. What's that graph look like? The graph of y equals 6. Oh. Yeah, a horizontal line, right? Let's just confirm that. So to graph things in polar mode, you'll press the mode button and change it to from wherever you're at to polar. POL is the abbreviation for polar. I would change back to radian mode. And then if we want to graph this, we'll do 6. And we don't have a cosecant button on our calculator, so I'm just going to do divided by sine theta because I know that 1 over sine and cosecant are the same thing. And then before I hit graph here, I want to turn my axes back on. I turned them off in a previous class to demonstrate something, so I'm just going to turn those back on. And it's been a while since I've graphed something, so I'm just going to do the good old Z standard. And whoa, look at that horizontal line. Shocking. But it looks just like we would expect it to, right? And you're saying to yourself, Mr. Kulik, it's so easy. Will it always be so easy? Well, maybe, but probably not. So what if we have r equals 6 cosine theta? So if you take a look at this, there's no way that we can directly get an r times cosine theta here, right? If I try to move cosine theta to the other side, I'd have to divide it. So I have r divided by cosine theta. That's not the same thing as x. If I tried to move the r to the right side, I have to divide by r. So I have cosine theta divided by r. That's not what I'm looking for. So how am I going to do this? Well, this is the trick. Just going to multiply both sides by r. You're like, oh, Mr. Kulik, you sly dog. That's a good trick. Because what do we notice that we get on the right-hand side? I now have an r cosine theta. What is that? Close, x, because it's cosine, not sine, right? And r squared on the other side. And wait a tick. Wait a minute. What is r squared? Holy smokes. This is pretty good. That's looking a heck of a lot better, right? If I have an x squared and a y squared in there like that, what kind of picture are we graphing here? Circle, quite good. Do you guys remember the equation for a circle? X minus h squared plus y minus k squared is equal to r squared. So what we're going to have to do then is get this equation that we have now in that standard form of a circle. So I'll just subtract that 6x over. Everybody's okay to hear? So the y squared is fine. Y squared is the same as like y minus 0 squared. So like, cool. But this, though, I have to make look like that. You did this last year. Does anyone remember the name of the process we used to do that? The abbreviations for the process is CTS. That stands for completing the square. So remember, for completing the square, the idea is we're going to take advantage of this perfect square factoring pattern. That we know that, for example, a plus b quantity squared is equal to a squared plus 2ab plus b squared. So if we take a look at what we have here, my a squared is going to be like my x squared. So a is what? X, right? If a squared is x squared, then a just has to be x. Everybody's okay with that? And then if I take this to be my 2ab, negative 6x is 2ab. So what that tells me is that if a is x, then negative 6 is just 2b, correct? So what's b? Negative 3, right? Everybody agree with that? So that's what I'm going to do, is I'm going to add negative 3 squared to both sides. Actually, let's write that as negative 6 over 2, so it'll be a little bit easier to see maybe where I'm getting that from. Okay. Now, x squared minus 6x plus negative 6 over 2 squared, that factors like a perfect square. Immediately, you don't have to think about it, just a plus b squared. Why does it factor like that? Because we made it factor like that. That's the whole point of the completing the square, right? So you take part of a quadratic, you tack onto the end whatever you need to make it a perfect square, and then it factors. That's the point, right? Cool. And then we have our like y minus 0 if you'd like. And then instead I'm just going to write that as 9. Negative 6 divided by 2 is negative 3. Negative 3 squared is 9. So this thing should be a circle centered at 3, 0 with radius 3. Everybody agree? Let's take a look. 6 times cosine theta. Whoa! Sure looks like a circle centered at 3, 0, radius 3. Okay. So I get it, Mr. Kulik. Sometimes I can get away just using identities to rearrange things. Sometimes I might have to do this completing the square thing. All right. Is there a way to know? You know, you could graph the thing in advance, and if it's a straight line, you shouldn't have to complete the square. If it's a circle, you have to complete the square. Oh, okay. Well, that seems okay. Mr. Kulik, does it get worse than this? Well, I mean, maybe a little. Let's do one more example. And you might have said, Mr. Kulik, hey, if I'm going to graph this anyways, like, why not just graph it in the beginning, look at the picture and be like, okay, I can write the equation for a circle with center 3 and radius 3. Like, that's not difficult, right? Will it always just be like that easy? Nah, man. And in fact, if your teacher's clever, they can disguise the problem so that, like, the picture doesn't really look like the answer. Oh, no. Mr. Kulik, are you that clever? Yeah. Okay. So let's take a look at C. This looks a little bit different, right? Notice that there's going to be no direct way to combine like the r and a cosine theta and r and a sine theta to get like r times cosine theta, r times sine theta, right? So we're going to use the same trick we did before and multiply both sides by r. And just like we've noticed before, I have an r squared. That's x squared plus y squared. I have a r cosine theta. So let's use a different color maybe. That's an x. And I have an r sine theta. That's a y. So I'll go ahead and make all those substitutions right now. So far, so good. Just like before, I'm going to move everything onto one side since I observed that this is definitely going to be a circle. I'll group the x's together and the y's together so that when I complete the square, it's obvious to me at least what I'm doing. So if I complete the square for x squared plus 5x, what am I going to have to add to both sides? Five over 2 squared, right? Everybody agree? Okay. And then what about the other piece? What am I going to have to do there? Negative 4 over 2 squared. Where is the 2 coming from?
That makes it 0.5.
So if I go back here, it's b over 2a. So like the negative 6 is 2b. So it's always going to be just dividing by 2 to that x coefficient. Yeah. Now, I said always. I need to put one little caveat on that. As long as the leading coefficient is 1, it'll always just be dividing by 2 to that middle term. If the leading coefficient on x isn't 1, then it's a little bit more trickier than that, but we're not going to cover that situation in this course, so don't have to worry about that. So x squared plus 5x plus 5 over 2 squared, how does that factor? Just a plus b squared, right? Is everybody okay with that? Who can tell me the next one? How does that one factor? Yeah, I'm going to write that as, it'd be y plus negative 4 over 2, but I'm just going to write minus 2. Uh-oh. I should have. You guys got me talking, and then I forgot to do all the color coding I meant to do here. Let's do that. And then I forgot to do it over here, like a big dummy. All right. So this here, it's a circle. The center of that circle is negative 5 over 2, 2. And the radius is the square root of 41 over 2. Right? Everybody can see that? This is an example where had we started with the picture, and that's it, trying to come up with that precise of an equation from just the picture, I don't think you're going to be able to do that. That's pretty tough. Just to find 4, what do you need? You need, well, I guess you need 2 rational points on that circle somewhere. Is going to be maybe not that easy to come up with. You know what I mean? That's why doing this process and not just going straight from the picture becomes maybe the easier way of doing it in the long haul. Everybody okay? What if we want to do the reverse direction? What if we want to go from rectangular function to polar function? Well, let's start with something easy. Say y equals 4. Well, that's pretty easy. What's y? R sine theta. Yeah, that's correct. So to get the polar function, typically r is the independent variable, so we write it by itself. So divide both sides by sine theta. You could stop there, or you could observe that, hey, 1 over sine theta is just cosecant theta. But either of those is fine. What if we give you something a little bit worse? Is this that big of a deal? What should I do?
Basically, the reverse of what we did.
Great.
Get it to the circle, like the square. And
Okay, so what's the reverse of that then? No. No. What? Why can't you square root that?
It's its own function inside of parentheses, and it's
the sum, right? You can't square root pieces. You'd have to square root the entire side, and then with the sum there, it doesn't really help you. What would we do? What can we do with this? It's already factored, guys. I think you're thinking of a different F word. Not that F word. Foil, yeah. So when I FOIL this out, this is what I get, right? This is what I'd write, correct? Who says yes? Who says no? Everybody but Jackson fails for not raising their hand. This is no. This makes Mr. Kulik very sad. He doesn't need any help being sad. He's plenty sad all on his own. He doesn't need your help. Please don't do this. What did we do wrong here? You distributed exponents, right? Why am I making a big deal of this? Because I looked at the homework quizzes from last time and saw a whole lots of distributing exponents going on. Oh, it's so sad. What should we be doing? Foiling. That makes Mr. Kulik much happier. Okay, so we foiled it out. Now what should we do? Okay. What terms do you see? No, I'm just asking. Okay. Why don't we just do this then? Well, that's fine. Why don't we just do that though? Right? Since the other side's 45 also, just move it all to one side so it's zeroed out. Is that okay? What else? Lots of things still. I don't really want to move them right now. I think they're good right where they're at for the moment. And you're not sure. Jackson?
Change x squared plus y squared to r squared.
Yeah, x squared plus y squared is r squared. That's great. Remind me again, what's x? R cosine theta. Oh, cool. And then we still got this y over here. What's y again? R sine theta. Ooh. We got rid of all the x's and y's now. That's pretty nice, right? Okay. We got to get the r by itself, though. Mia, what do you want to do now? Now let's move that stuff to the other side. So I'm going to leave the r squared over there. But the other 2 I'm going to put on the other side. Then what? We have an r squared on the left. What do we need to have there? Just an r. What should I do to get rid of the squared? You might think that, but that's going to be a problem because now this whole side has a square root over it that we're not going to be able to simplify. What was that? Divide by r. So you want to do something like this? You made the suggestion. Yeah, that is what you want to do. But wait a second, Mr. Kulik. I remember you've told me very clearly not to divide by variables ever.
Yeah.
Right? Why is it okay in this situation? Why can't r be 0? That's correct. That's why we don't divide by variables, is specifically because they can be 0, and if they are, you're dividing by 0, and that's very bad. But we know r is not 0 here. Why? It's a radius of what? Of this circle. Does that circle have a radius of 0? Definitely not, right? Well, it would be a non-zero radius, so we are in the clear. So it's no big deal. Oh, well, that actually, Mr. Kulik, might have been easier than the completing the square one. All I had to do was FOIL everything out and convert the things into R's, use my formulas again. I didn't have to do any sneaky algebra there. Really, like that was almost easier than the other ones were. I think it might have been actually easier than having to do the completing the square, which is nice. I wonder what this looks like. What, are you confused? It looks like the circle whose center is at 3, -6 and its radius square root 45, guys. Come on. You know what it looked like beforehand. Is that okay? We okay? Everybody's cool? All right. Section 10.5, we're going to be talking about the graphs of some polar function. And the first thing we're going to talk about here are mins and maxes, domain and ranges, and like symmetries. So let's just start with the easiest thing to do. Let's take a look at this guy, 3 plus cosine theta. If I'm looking for the min and max, I can do this without a calculator. It's actually easier to do it without a calculator. How would I do that? What do you mean, Mr. Gulick? How can I figure out the minimum and maximum for there's no calculator? You don't need it, man. It's easy. What's going to determine the minimum and maximum value for R here? The values of cosine theta, right? What are the possible outputs of cosine theta? That is correct. So the minimum for R would just be where cosine theta is -1. And the maximum value for R would just be where cosine theta is +1. So easy, Mr. Kulik. Yeah, no doi. So what's the range for R then? Just 2 to 4. Oh, okay. Sure. Yeah, that's cool. No biggie. Yes, sir. Yeah, of course. Mr. Kulik, does it get sneakier than this? I mean, not really. Not for the things I'm going to ask you to do anyways. I mean, it always gets sneakier than this, but like, what if we have R equals 4 minus 3 sine theta? Well, I'm going to be doing the same thing. Really, the value for R is dictated by sine theta here, correct? And what are the possible values of sine theta? -1 to 1. Yeah. So my minimum occurs when sine theta is equal to what value? +1. And the maximum occurs when it's equal to -1. Whoa, 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 Mr. Kulik. Why are they flippy-floppy there? Well, because there's a negative sign in front of the sine. So it's really like the opposite. You know what I mean, guys? So my range for r in this case is just going from 1 to 7. Whoa! Everybody okay with that? What would the domain be for this, for any of these? Domain's going to be concerning which variable, r or theta? Theta! And you knew that because we already talked about range was for r, right? I wrote it down on the board there twice. Which is good. You're paying attention. What value? So what's going to determine the range or the domain for theta is just what things can we plug into sine or cosine. What values of theta? What was the domain for the sine function and cosine function? We did this already last semester. These are fundamental things we should remember. It's super easy. All real numbers. Right? What kind of angle can you plug in for sine and cosine? Anything! Right? That's we spent all first semester building out sine and cosine's definition so you could literally plug any number into them. You guys remember doing that? We built out the unit circle and then we extended it to deal with negative angles and things that were bigger than, coterminal things, and we plug whatever you want into it. The domain's always going to be all real numbers for these things. They have a sine or cosine in it. Unless you're dividing or something by it, but we won't see that. All right. Let's talk about symmetries here. Just like we did in first semester, we'll talk about 3 types of symmetries. We have symmetry to the x-axis, we have symmetry to the y-axis, and then we have this alpha degree point symmetry with respect to the origin. So to show something is x-symmetric, we're just going to replace r theta with r negative theta and show that we still get the same thing. To show that something is symmetric with the y-axis, we're going to replace r theta with r negative theta and show we still get the same thing. And to show that we have this alpha point symmetry, we're going to replace r theta with r theta plus alpha and show that we'll still get the same thing. So let's just do a little example here. So let's say we want to prove that r equals 5 sine 3 theta has x-axis and 120 degree point symmetries. I'm going to do that 2 separate proofs. So to do the x-axis symmetry, I'm going to be replacing r theta with r negative theta. Uh-oh. Somebody needs to be paying attention and not checking their fantasy basketball scores or something. I don't know. That's what you're doing. I'm just guessing. Was I right? Oh. It sounded like an ad for... No,
honestly, if I could customize my notifications thing, I just have it to the old dial-up "You Got Mail" sound.
Everybody's okay with what I did there? So I've just replaced the theta in my old equation with negative theta, right? Which is what we're describing doing here. Okay. Well, let's simplify this then and try to get the same thing we started with. 3 times negative theta is negative 3 theta. And then, aha! I notice an identity that I can use here. Oh my goodness. Great googly mooglies. This was supposed to be y-axis symmetry because it doesn't have x-axis symmetry, Mr. Kulik. Way to go and confusing everybody. You know, just stop being so hard on yourself. It happens. People make mistakes. Zhoosh. So I did this, I did this, I did this, and I did this. Sorry for the edits. It's in green. The only edits are in green. I know. It's hard enough, Mr. Kulik. Stop making mistakes. I have it written down in front of me. I just made a mistake. Cut me some slack, Jack. Like, you don't ever make any mistakes. I've seen your papers. No? Okay. Anyways, doesn't change the reasoning. I see an identity I can use. Does anybody can tell me what identity it is? It's one of the odd-even identities. Sine of negative theta is equal to negative sine theta. That's what I'm using here, which allows me to pull that negative sign that was inside my sine out to the front. And if I divide both sides by -1 now, I'm back with the exact same thing I started with. So I'm done. I've shown the symmetry. Yay! So, to do the 120-point symmetry, the R is staying the same. But this time, my theta is going to be replaced with theta plus 120. We all okay? Well, I'm going to distribute that 3 through. And ask you the same question. Does anybody see an identity I could use here? Ooh, I do. Don't we have an identity for the sum of 2 angles when we're doing the sine of the sum of 2 angles? Actually, let's make that. We'll write both versions. Look at that, right? Who remembered that one? Shame on you guys. You need to remember that. We did this. We did it. There's no forgetting allowed. I know that's a tough standard because, Mr. Kulik, you make mistakes all the time. I know. But, like, you got to strive for perfection, and maybe sometimes you'll just land in greatness instead. Perfection's tough to get there, but it's the trying that matters. Okay, so I use that identity. All right, now what, Mr. Kulik? What do you guys see? Oh. Cosine 360. I know what that is. What is it? 1. All right. And what's sine 360? 0. So that stuff drops off. And what are we left with? Exactly what we started with, the original equation. Woohoo! We did it! Oh, that's pretty neat. What did you guys think? Was that fun? It was kind of fun. In like a perverse kind of way. Drake.
So, what was the identity that you used specifically for the last few parts of getting a y-axis?
This?
Yeah.
Sine of negative alpha equals negative sine alpha. It's one of the odd-even identities.
Oh, yeah.
Okay. Well, let's take a look at what this weird sine 5 3 theta looks like, right? It's going to have some kind of crazy symmetry to it. Is it 120 degree point symmetry? What the heck does that even mean? Let's do it. Take a look. Whoa! Kind of looks like a flower, doesn't it? Like it's got 3 petals. It's a pretty flower. You can try smelling your calculator. It's just going to smell like your calculator, though. I know it looks so much like a flower, you're confused. It turns out that these types of graphs we're going to give a name to. We're going to call these guys rose curves because they look like flowers. Not really like roses much, but I didn't get to pick the type of flower that we're going to name it after. So our standard form for these are going to be things of the form a cosine theta or n theta or a sine n theta, where n is greater than 1 and it's an integer. So n has to be like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You get the idea. The domain, well, all it's got are sines and cosines in it, so, or sines or cosines in it, so the domain just has to be all real numbers. The range is going to be negative absolute value of a, comma, positive absolute value of a. Our mins and maxes, well, the min is negative absolute value a, and the max is positive absolute value of a. Mr. Kulik, you're blowing my mind right here, man. Well, you know. The number of petals, just going to be n. The symmetry, if alpha is 360 divided by n, if n is odd, then we have, all right, well, let's start with even actually, because there's only one case there. We got all the symmetries. We got x-axis, we got y-axis, and we have alpha point. If n is odd, and we're dealing with the cosine version, then we have x-axis and alpha point, but not y-axis. That was kind of funny sounding, wasn't it? I don't know really where that came from. If we're doing sine, we have y-axis and alpha point, but not, turned into a goat apparently, x-axis. So if we wanted you to analyze something like r equals 6 cosine 5 theta, we would identify, okay, this is a rose curve. The a is -6 and the n is 5. So we know that the domain is going to just be all real numbers. The range is going to go from 6 to, or -6 to +6, with a minimum at -6 and a maximum at +6. We have 5 petals. And since n is odd and we're of the cosine version, we know we have x-axis and 72-degree point symmetry. Mr. Kulik, 72 degrees, where in great googly moogly did you get that? Just 360 divided by 5. 5 being the number of petals. So that's like all we did. We just used the information from our table and just kind of copied it in there. Oh, boysies, let me answer that question in a moment.
Is that n or an r for equals 5?
A equals -6 and n is equal to 5. So if we looked at our picture here, this is our pretty flower. What does 72-degree point symmetry mean? If I rotate this 72 degrees, basically this petal would now be lying exactly where that petal is. That petal moves to where that one is, and that one, and that one, and they all just move one petal placement. You know what I mean? That's pretty neat. But okay, so just like all I'm doing is following some rules that I've written down. Is that it, Mr. Kulik? Well, no, there's another type of curve called a Limason curve. We're going to talk about those. And so this word Limason is like a last name for a mathematician or something. It's got that C with the little comma attached to it. I don't remember. What are those things called? Language people? Anybody know? Somebody Googled it second hour for me. I've forgotten already.
What
Which,
common thing are you talking about?
well, this right here, where it has like a little tail attached to the letter.
Oh.
That's what I'm talking about. I forget what those are called. They looked it up for me second hour and they told me, and I've forgotten already, which tells me how good I must have been listening to them. Which says a lot about Mr. Kulik. Okay, so my standard form for these is a plus or minus b cosine theta and a plus or minus b sine theta, where a and b are considered to be positive values. Again, the domain, since this involves either just sines or cosines, it's just going to be all real numbers. The range is going to be a minus b and then to b minus a. I'm sorry, a plus b. Sheepers creepers, Mr. Kulik. So our min and max are just a minus b and a plus b respectively. And now there's actually 4 different types of Limason curves, and they're classified depending on their value for values of a and b. So if a over b is less than 1, it's called an inner loop curve. If they're equal to exactly 1, this is called a cardioid curve because it kind of looks like a heart. I think it looks more like a butt. I'm just letting you guys, just being honest. If that a over b is between 1 and 2, this is called a dimpled. I think it looks a lot like the cardioid, but the crack isn't quite as deep. And then if a over b is greater than or equal to 2, this is convex. Basically, it means it looks like a circle. And then the symmetry is really easy. Basically, the cosine one gives, it has, has x symmetry, x-axis symmetry. And the sine one has y-axis symmetry. So let's look at these different couple of pictures here. I'm going to fix my window a little bit so it produces us a decent picture. This is why I had the axes turned off earlier, so it's easy to see these things. All right, so let's say we have 1 plus 2 sine theta. There, a is 1, b is 2, so that should be 1 over 2. So if I graph that, that should give me the inner loop. See the little loop on the inside? That's what inner loop looks like. If I change this to, I'm going to do 2 and 2, that should be a cardioid. So there's my heart shape. Still looks like a butt to me. A butt print anyways, you know. Okay. A dimpled would be between 1 and 2. So it's, how about 3 over 2? That's should be dimpled. See, there's my dimple right there, just like a little curved indent. Like golfers out there, the dents on your golf ball are dimples. Same idea here. We got one little dimple right there. Or those people with nice smiles, you know. Or let's say there's 5 over 2, so that would be greater than 2. This would be convex. It basically just looks like a circle. There's no indents or divots or, you know, dimples or cracks or anything in there. Everybody's cool with the pictures? So let's do one quick example. Okay. So if we want to analyze r equals 4 minus 3 sine theta, I notice this is a Limason curve where the a is 4 and the b is 3. Notice that the b is not negative 3 here. The a and b are always positive values. So my domain, well, since it only depends on sine or cosine, I know the domains are always going to be all real numbers. The range is A minus B, comma A plus B, or really just 1 to 7. Well, my min and max values are R equals 1 and R equals 7 respectively. The type here, so my A over B is equal to 4 over 3. And since that is between 1 and 2, that should be the dimpler. And then the symmetry, since it's the sine one, it should be y-axis symmetry. And we could confirm all of this if we like by looking at the picture. 4 minus 3 sine theta. I guess some is a little bit off the screen, but there's my dimply doodad. Still kind of looks like a butt. But that's just me. Everybody feel okay? Overall, this was, I think, easier than the parametric chapter, or the parametric stuff. I think that's the harder part of this chapter. The polar stuff is pretty plug and chuggy. Mac.
When you graph this, is it in polar mode?
Yes. Graphing all these things in polar mode. So that does it for us. That cleans up this chapter. So what we can do now, we can go all the way to 96. So 63 to 96 will be the next problem set. Next time, we're going to do our review day. And then we're going to, per popular request, we'll start chapter 11 on Friday. And we'll do the test next week on Tuesday. With respect to those of you that are like musicaling your brains out here this week.
So
Sound fair?
Wednesday is
Review. Or if you'd rather switch, we can do the review day on Friday and do chapter 11 on Wednesday. It doesn't make much of a difference to old Mr. Kulik. He's cool doing whatever order you guys feel like. We don't have to make a decision right now. We can just play it by ear. How's that sound to you guys? Pretty reasonable, I hope. I try pretty hard while having high expectations.